There's a couple questions, but I was just, I don't even know what you're trying to say. I don't know what they're trying. It's very much. How do you expect it not to? Yep. But the chemistry test I took immediately following those two was good, so we ended the day off. I had the same thing, the computer science test I took later that weekend, it's fine. There we go. That's, you know, are you a computer science major? Do you like it then? Do you like it then?
I like it. I'm not very good at it.
My dad does that, and I took a high school course in it, and I literally couldn't do anything. It was like, I don't think I inherited that gene.
We'll start in about a minute. Today we'll start chapter 10, section 1 on curves defined by parametric equations. So as you know, some curves in the xy plane cannot be represented by an equation of the form y equals f of x. But many of those curves can be represented parametrically with parametric equations. So just to illustrate that, if you have some curve in the xy plane that does not pass the vertical line test, then this curve cannot be represented by a function of the form y equals f of x. But there may be parametric equations that define that curve. So let's suppose the x and y coordinates of a curve C are both functions of a parameter, a third variable t, where the x coordinate x is f of t and the y coordinate is g of t. So those equations, x equals f of t and y equals g of t, are called the parametric equations of the parametric curve C. So in this picture, we have a curve C, and we're supposing that each point on that curve with coordinates x, y are determined by parametric equations f of t and g of t for t in some interval. Okay, so each value of the parameter t in the common domain of the functions f and g corresponds to a point xy equals the ordered pair f of t, g of t on the parametric curve C. So as t varies, the parametric curve C is traced out by the points f of t, g of t. Okay, in some applications, the parameter t is a measurement of time, and the point f of t, g of t on a curve is the location of a particle at time t. So in those cases, the direction of the particle as it traces out the curve is easily determined. Okay, the curve C with parametric equations x equals f of t and y equals g of t for values of t between a and b, it has an initial point, f of a, g of a, and a terminal point, f of b, g of v. So here's our first example. Identify the curve in the xy plane that is represented by the parametric equations, and then indicate the direction that the curve is traced. One way to go about this is what I do almost all the time, is I'll list a column for t values, and then two more columns for x values and y values. And then plot the points, plot the ordered pairs x, y. And then after I have a number of points, I'll just connect the points. So our t interval begins at 0. And when t is 0, x is sine of 0, which is also 0. And the y-coordinate cosine of 0 equals 1. And then what you choose to decide, some might choose to be more detailed, while others are less detailed. To start with, I'll be a little bit more detailed. If I pick t to be pi over 6, which is equivalent to 30 degrees, sine of pi over 6 is 1/2. cosine of pi over 6 is the square root of 3 over 2. Then I can pick t to be pi over 4, or the 45-degree angle. Sine of pi over 4 is square root of 2 over 2, and cosine of, which is the y-coordinate, cosine of pi over 4 is also the square root of 2 over 2. So at this rate, we're not going too fast if we go all the way from 0 to 2 pi, but I'll start to pick fewer numbers as we go. But if we pick pi over 3, sine of pi over 3 is the square root of 3 over 2. Cosine of pi over 3 is 1/2. And then pi over 2, sine of pi over 2 is 1, and cosine of pi over 2 is 0. So this is only 1/4 of the way between 0 and 2 pi, but let's go ahead and plot those points in the xy plane. The initial point, 0, 1. And then 1/2 square root of 3 over 2. Square root of 3 over 2 is a little bit bigger than 0.85. So it's about there, say. Square root of 2 over 2, that's about 0.7. Square root of 3 over 2. And then 1, 0. Okay, so what shape are we getting, do you think?
Circle.
Yeah, circle. This is the first quarter circle. And we'll indicate with an arrow this doesn't really look like a quarter circle, but indicate with an arrow the direction of the curve. So if we were to plot more points, we would get the full circle. So I'll just list a few more t-values, not the whole list, but so after pi over 2, we could pick, let's just jump to pi, and then 3 pi over 2 and 2 pi. So when t is pi, sine of pi is 0. Cosine of pi is -1. So we're down here at 0, -1. This point is 1, 0. 3 pi over 2, sine of 3 pi over 2 is -1, and cosine of 3 pi over 2 is 0. So that gets us to that point, -1, 0. And then when t is 2 pi, sine of 2 pi is 0, and cosine of 2 pi is 1. So in this case, the initial point and the terminal point are the same, but we're just tracing out a circle clockwise. So pretend like that's a circle. This problem doesn't ask for a Cartesian equation, but I'll go ahead and write down an equation for this curve in terms of x and y. So note that if we square x, x squared is equal to sine of t squared. And if we square y, we get y squared equals cosine of t squared. And one of our Pythagorean identities, sine of t squared plus cosine of t squared equals 1. And so the equation for this curve in Cartesian coordinates is just x squared plus y squared equals 1. And we do recognize x squared plus y squared equals 1 as the equation of the circle centered at 0, 0 with radius 1. That's the same circle that we got with the parametric equations. One key difference is in Cartesian coordinates alone, we don't necessarily identify the direction as the curve is traced out. But when it's defined parametrically, if we need the direction, we can determine the direction by the values of t as they go from small to large. Okay, the next example, before the next example, we have a statement or a note. I guess we haven't done anything yet to make note of this, so this is just a statement. A set of parametric equations used to represent a curve in the xy plane is not unique. So in other words, there may be, and there often are, different ways to write parametric equations for a curve. So in this example, identify the curve in the xy plane that is represented by the parametric equations and indicate the direction that the curve is traced. So the parametric equations are x equals cosine of pi times t and y equals sine of pi times t. And the values of t are from 0 to 2. Okay, we'll list a few of the ordered pairs that correspond to t values. So starting with t equals 0, when t is 0, x is cosine of 0, which is 1. And sine of 0 is 0. And if we pick t to be 1/2, cosine of pi halves is 0. Sine of pi halves is 1. And if we pick t to be 1, cosine of pi is -1. Sine of pi is 0. Pick t to be 3/2. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is -1. And then when t is 2, cosine of 2 pi is 1, and sine of 2 pi is 0. Hey, there's a lot of other points that we could have plotted. So let's just plot these points. So 0 or 1, 0. This is our initial point. Then 0, 1. Then negative 1, 0. Zero, negative 1. And then 1, 0. So our initial point and terminal points are the same. What does the curve look like in between those points? It's going to be a circle. Yeah, if you're not sure, like if you're tempted to write straight line segments in between those, then it might be, you might want to pick more points so that you'll conclude that this is it's a circle. So pretend like that's a circle. This time the orientation of the curve is counterclockwise. Okay, but this is the same circle that we got in the previous, with the previous parametric equations. We had a different starting point or initial point. And in the other example, the orientation was clockwise. This time it's counterclockwise. When you convert to Cartesian coordinates, you still get x squared plus y squared equals 1. Okay, so one of the takeaways from these first two examples is this note up here. One set of parametric equations for a curve is not the only set of parametric equations, as we saw in those two examples. Okay, the next one, sketch the curve defined by the parametric equations x equals t to the second and y equals 2t plus 3. Then after that, we'll eliminate the variable t and write an equation for the curve in terms of x and y. But first, pick some t values and then find the corresponding x and y coordinates. We don't always have to assume that t must be non-negative. So I'll pick a few negative values for t. I'll start at -2 and then increase by 1. So let's try those 5 t values. When t is -2, the x coordinate is +4, and the y coordinate is -1. When the t coordinate is -1, the x coordinate is +1, and the y coordinate is also +1. When t is 0, the x coordinate is 0, and the y coordinate is 3. When t is 1, the x coordinate is 1, and the y coordinate is 5. And then finally, when the t coordinate is 2, the x coordinate is 4, and the y coordinate is 7. Okay, we'll plot those points. Okay, the first point, 4, -1. And then the point 1, 1. 0, 3. One, 5. And 4, 7. So if we trace those, well, we're missing some information, but looks something like this. And then indicate with an arrow, let's see, for smaller values, so our arrow is in that direction. That's the orientation of the curve. So this might not be an extremely accurate graph of the curve. If we want more accuracy, we can pick more t-values. But it sort of looks like a parabola. Okay, so let's eliminate the variable t. So any suggestions on how to write the Cartesian equation in terms of x and y only without the variable t?
Could you solve for t in both equations and set them equal to one another?
Yeah, it might be more efficient if you solve for t in one of the equations and then substitute that into the other equation. So what you said can probably work. We would just have to make sure that we take into account the fact that this t is squared. So what I suggest is solve y equals 2t plus 3 for t, and then afterwards replace t in the other equation with what t is equal to from this one. Okay, so if we subtract 3 and divide by 2, we get t equals y minus 3 over 2. And then in the other equation, replace t with y minus 3 over 2. So this is probably an okay equation, even as it is. We could write it as y minus 3 squared over 4. But we know that this is a parabola. It's x is a degree 2 function of y. But you can multiply it out too if you want. So yeah, x is a quadratic function of y. Yeah, so it looks like the curve is actually pretty accurate. When y is 3, the x-coordinate is 0, and that's the vertex. So. Okay, the next example, I decided after I sent the lecture notes that this example is sort of lame, but we'll go ahead and do it. Sketch the parametric curve defined by x equals secant of t and y equals tangent of t for values of t between negative pi over 4 and pi over 4. So if anything, we'll get a little bit of practice with trigonometric evaluations. So starting at negative pi over 4, and then we'll go to negative pi over 6 and 0, pi over 6 and pi over 4. That ought to do it. Hey, so if t is negative pi over 4, the x-coordinate is secant of negative pi over 4. So secant of negative pi over 4 is the reciprocal of cosine of negative pi over 4. And cosine of negative pi over 4 is just 1 over the square root of 2. Square root of 2 over 2, which is 1 over the square root of 2. So the reciprocal, which is secant of negative pi over 4, is the square root of 2. So are we all in agreement? The tangent of negative pi over 4, negative 1, right? Okay, secant of negative pi over 6, well, cosine of negative pi over 6 is the square root of 3 over 2. So the reciprocal is 2 over the square root of 3. 2 over the square root of 3. The square root of 3 is about 1.72 or so. So 2 over 1.7 is a little bit bigger than 1. So I see that you agree that this is a lame example. Okay, the y-coordinate when t is negative pi over 6, tangent of negative pi over 6. Well, that's sine of negative pi over 6 over cosine of negative pi over 6. So sine of negative pi over 6 is negative 1/2. Cosine of negative pi over 6 is the square root of 3 over 2. So this is negative 1 over the square root of 3, right? Okay, this one will be easier. When t is 0, secant of 0, cosine of 0 is 1, so the reciprocal is also 1. Tangent of 0 is 0. And then for the positive values, pi over 6, cosine is still positive, so it'll be 2 over the square root of 3. Tangent of pi over 6 is 1 over the square root of 3. And secant of pi over 4 is the square root of 2, and tangent of pi over 4 is 1. So let's go ahead and plot those points. Okay, so the square root of 2 is about 1.4. and -1, so we get this point. This is our initial point. 2 over the square root of 3 is a little bit bigger than 1, and minus 1 over the square root of 3 is about roughly negative 2/3. And then 1, 0. And then on the other side, 2 over the square root of 3, 1 over the square root of 3, and then square root of 2, 1. So this is it. This is the curve. The direction is that way, but we have an initial point at square root of 2, -1, and a terminal point at square root of 2, +1. So that's that example. The next one will be a little more interesting. Sketch the curve defined by x equals 1 over the square root of t minus 1 and y equals 1 over t minus 1. On this one, note that the t values must be strictly greater than 1. So let's pick a few t values and find the corresponding x and y coordinates. So we can get as close to 1 as we want, well, in theory. So I'll pick t to be 1.01. And the x coordinate, 1 over the square root of 1.01 minus 1. That's 1 over the square root of 0.01. 0.01 is just 1/100th. And the square root of 1/100th is 1/10. And 1 divided by 1/10 is 10. So the x coordinate is 10. And the y coordinate, so 1 over 1.01 minus 1 is 1 over 0.01, or 1 over 1/100th. And 1 over 1/100th is 100. So when x is 10, the y coordinate is 100. Yeah, we can get closer to 1 than 1.01, but I'm going to pick larger values for t. Let's pick t to be 2. So the x coordinate is 1 over the square root of 2 minus 1, or 1 over the square root of 1, or 1. And the y coordinate is 1 over 2 minus 1, which is also 1. And let's pick some other convenient values of t so that we can easily find square roots. If we pick t to be 5, then 1 over the square root of 5 minus 1 is 1 over the square root of 4, or 1/2. And then 1 over 5 minus 1 is 1/4. So just one more ordered pair. How about if we pick t to be 10? So 10 minus 1 is 9, square root of 9 is 3, so 1 over 3. And then 1 over 10 minus 1 is 1/9. Okay, so if we plot these points, 10 over 100 is off the grid, so but we do have 1, 1, and then we also have 1/2, 1/4, and 1/3, 1/9. So what's the shape of the curve? Notice if you look at the x coordinates and compare them with the y coordinates, the y coordinate here is 100 is 10 squared, 1 is 1 squared, 1/4 is the number 1/2 squared, 1/9 is the number 1/3 squared. So it kind of looks like y equals x squared. So what we have is part of a parabola what's the direction of the curve? We don't have an initial point because the t values can be made as close to 1 as we want from the right-hand side. So there's no initial point. So it's way up there, but the direction of the curve is downward. And since t never can actually get to 1, we're going to have an open circle at 0, 0. But in the abstract, the curve gets as close to that point as you can, or as you can think of, without actually getting to the point. So that's the graph of that parametric equation. Okay, this one is if you want to write the Cartesian equation, notice that since x is 1 over the square root of t minus 1, y is just x squared. Because when you square 1 over the square root of t minus 1, you get 1 over t minus 1. But we would say, to make it conditional, x is strictly greater than 0. X can't be 0 itself because of how it's defined up here. Okay, let's move on to the next example. This one says, for the set of parametric equations below, eliminate the parameter to find a Cartesian equation of the curve and graph the curve. Okay, if we do that first, if we solve y equals t minus 1 for t, we get t equals y plus 1. And then in the other equation, replace t with y plus 1. So we have y plus 1 squared plus y plus 1. And we just get x expressed as a quadratic function of y. So x is equal to y squared plus 3y plus 2. Okay, since our t values are restricted, we'll want to find the initial point and the terminal point. So when t is -3, let's find the x coordinate and the y coordinate. When t is -3, the x coordinate is 6. And the y coordinate is -4. This is our initial point. The terminal point at 2, the x coordinate 2 squared plus 2 is 6. And the y coordinate 2 minus 1 is 1. So this is our terminal point. So we can find the intercepts. So x will be 0 when y is -1. I think I made a mistake somewhere. Oh. Not yet, but almost. Okay, so one of the y-intercepts is -1, and the other one is -2. So it's a parabola that looks something like this. Let's find the x-intercept. So the x-intercept is 2, 0. So in other words, when y equals 0, x equals 2. You can see that from there. So this is the direction of the parametric curve. Okay, in the next example, sketch the curve defined by the parametric equations by eliminating the parameter. Okay, so on this one, if we just solve y equals 3t minus 2 for t, solve for t. So we get t equals y plus 2 over 3. And then we get x equals the square root of y plus 2 over 3 minus 2. And if we simplify what's inside this square root, this will become the square root of y minus 4 over 3. Hey, so how do we graph that? So is this what we want? So I'm going to plot a few points parametrically first. So the t-values have to be greater than or equal to 2 since x is the square root of t minus 2. So the smallest t-value is 2. The x-coordinate is 0, and the y-coordinate is 4. And then if we pick t to be 3, square root of 1 is 1, and 9 minus 2 is 7. So the ordered pair 0, 4 is a point, and 1, 7. One, 7. So let's see, one more t-value. How about if t is 6, square root of 4 is 2, and 18 minus 2 is 16. So the graph looks something like this. We know that if x equals the square root of y minus 4 over 3, then it's half of a parabola. Okay. So that is one way to write the Cartesian equation, but I think another way, if you solve for t on the left by squaring both sides, so we get x squared equals t minus 2, so x squared plus 2 equals t. And then in the other equation, replace t with x squared plus 2. So we get y equals 3x squared plus 6 minus 2, or 3x squared plus 4. So I think I botched this graph here. So since we're about out of time, tomorrow we'll start with this one again. I'll redo this one. Redo this. Yeah, I think this is the better way to look at it. So since we have a few seconds, y equals 3x squared plus 4. Is a parabola that opens upward, but we do have restricted values, so x can only be greater than 0. So it's half of a parabola, not a full parabola because of the restricted values. So this is just for x greater than or equal to 0. Okay, I don't think we need to redo this one. This is just half of a parabola for values of x greater than or equal to 0. Okay, that's all for today.
So, I'm obviously too stupid to do it this way.
What's that?
I'm obviously too stupid to do it this way. Do you know of like any tutors I can get or something like that? Or
Have you tried the math center?
I found they're not usually very helpful with calculus.
Yeah, that's not surprising, but
Um,
I don't know of any tutors.
for like any master students or something.
What's that?
Any master